And thank you for the introduction. I hope you can actually hear me. I also appreciate making this extra effort for allowing me to present online. Unfortunately, I'm not in the country, so I couldn't be there in person. So let's get started about the talk today. So today I'll be talking about GPU computing meets persistent memory. I intentionally chose this topic because it has the term persistent, and this is my way of saying thank you to the Persistent Foundation, which has been a great supporter for ACM and also for this award. So thank you. With that, let's get started. But before I actually get into the technical details, it's a little bit about what we actually do at Computer Systems Lab at IISc. So whenever we are thinking about digital computing system, what we are trying to do is trying to solve a computation problem by actually moving electrons. And the transistors work as switches to actually control the movement of the electrons. And there are tens and billions of such transistors in a computing system. Of course, it is very hard to really think about solving a computation problem by managing those tens and billions of transistors. So what we have actually done is in computing that we have actually created a stack, right? Whenever we are, can you actually hear me? Well, I saw. Okay, fine. So whenever we wanted to solve a problem, we think about the algorithm. We actually encode that in an algorithm in a programming language. Then the compiler comes that actually translate the human understandable code to that's something that the system can the hardware can understand. There are runtime systems to actually manage the system, and then there is actually hardware, the architecture, microarchitecture, and so on. So when you say computer systems research, it is the middle part of the stack. That is what we generally refers as the computer systems research. And it is interesting because it has a wide impact across application. Even if you improve the system by 1%, all the application that is actually running on that system, or everyone sees that improvement. And it influences other areas of research. For example, the ML AI could actually happen because GPU happened, right? And in our lab, we are particularly interested in looking into how the software is evolving and its needs are evolving, and how new technology trends are emerging from the bottom of the stack to actually meet them together and create new innovative systems. So that's an example you will actually see in this talk. Okay, so what's coming? This is the high-level agenda. So those who are not initiated on why we use GPUs for parallel computing, I'll give you a brief background. Then we'll actually spend most of our time talking about the primary topic of this talk, which is how the GPU computing and persistent memory, these two seemingly unrelated technologies, why we actually put them together, how we actually put them together, and then we will spend maybe a couple of slides talking about how we actually extended that to use even CPU and GPU together for important classes of application. Okay, let's now get started on the technical side of the talk. So I think it is not a news to anyone that we are generating exponentially more amount of data. So this particular graph shows that how over the year, the amount of data that we are actually generating has actually been increasing. Every time we actually click on a like button or make a financial transaction, we generate new data. This data has knowledge embedded in it. For example, that can be used as providing a targeted advertisement. But to generate actionable knowledge out of this big amount of data, it also requires a lot of compute. I argue that you need a lot of parallel compute to compute on such a big amount of data. And that's why the GPUs come in, because GPUs has become, or graphics processing unit, they have actually become the accelerator of choice for data parallel computing. Of course, they're the backbone of in AI ML, but that's not the only area. The scientific computing, weather forecasting, and so on, graph processing, data clustering, warehousing, you name it, all kind of software ecosystem today rely on GPUs for their primary computing needs. So one may actually wonder, the full form of GPU is graphics processing unit. So how come it became an accelerator for parallel computing? So we'll actually start there at a very high level. So whenever you're thinking about graphics, it's about pictures, right? And transforming the pictures. If you're thinking about playing video games, like it's videos are nothing but a stream of pictures. And these GPUs are designed to actually process on those pictures. And what is a picture? Picture has a lot of pixels, right? So what originally the GPUs have been designed for and optimized for is to actually operate on each of these pixels in parallel, because you typically do identical operation or computation on each of these pixels. Now you think of these pixels are replaced with data items or numbers. They look like matrix, right? And this is what really actually happened, that the GPUs became really good for data parallel computing, where you do the same operation on many data items in parallel. And the serendipity is that ML and AI needs a lot of matrix and vector arithmetic, and that led to the GPU boom. So at a high level, this is why the GPUs became the platform of choice for data parallel computing. And just to give you a sense of when you talk about the parallelism in the GPU, how much of parallelism it actually offers. Let's look at this in a graph. It actually shows on the x-axis the years, and the y-axis the number of parallel computation threads that one GPU can run at any given point of time. The points in this graph are different generation of NVIDIA GPUs and the number of concurrent thread, the parallel thread that can run at the same time. So we are talking about, say, today, more than 24, almost 25,000 threads that are running at the same time, that can run at the same time on a single GPU. And actually around 300,000 threads, GPU threads, that can be ready to run at a given time. So it's a massive level of data level parallelism. It's not like another large multi-core. While this evolution on the GPUs software stack has been happening, that a lot of software relies on the GPU, there was another trend that we also noticed, which is there is a need for fast persistence at internet scale. So what do we mean by persistence? The persistence is about making a data item durable across power cycle. For example, when you write something and force something out to the storage, not in the memory, but to the storage, then that actually can survive even if the system goes down or it is actually powered down. Writing to the memory is not, for example, in contrast, is not making something persistent. Now, why this need for fast persistence is actually growing is because every time we, for example, click something, as I say, like you generate some amount of data, or we actually go to, say, Facebook or Instagram, we want to actually access some data or update something. All this information needs to be persisted. You cannot forget. Okay, and for that you have many critical backend software system like Meta's RocksDB, Google's LabelDB. These are persistent key value stores where you can easily or quickly look up and update a data item uniquely identified by the keys. Then you have long-running applications such as DNN training that from time to time checkpoint their weights that it learned or the optimizer state. Because if the system goes down, you do not actually want to lose all the computation that you have actually started. You want to resume from where it actually failed. Also, it is needed to do a debugging. For example, how you want to figure out maybe the convergence is not started not working from after some point of time. And this is not new. The HPC world has been doing checkpointing their state for the long-running operation from time to time. And then, the transactions and the databases. For example, when you actually do fintech, some UPI, payment, you cannot actually, these are transactions, and these also needs persistence. You cannot forget about that. So the need of fast persistence at a very high scale, at an internet scale, is growing. At the same time, one of the things that we actually noticed, there is something also happening in the technology side where the new kind of persistent technology is actually coming up called the persistent memory. But before we understand what the persistent memory is, let us look at how the data is persisted at storage today. So let us assume that you have a piece of data that you want to actually read and update, and you cannot actually do that from the storage directly. So first you have to actually bring that data into the DRAM, and this would be done typically by the operating system at a granularity of many kilobytes, typically 4 kilobytes, and takes tens to hundreds of microseconds. Once it is there, the application software then can actually do load stores in the DRAM at nanosecond granularity and update this data. Once this data is updated in the DRAM, again, you need the operating system help to actually push this data down to the storage medium to make sure the data is persisted. This distinction between DRAM or the memory and the storage has been the cornerstone for how the software has actually evolved over the decades. But this key distinction is getting blurred with emergence of new memory technologies that we call persistent memory. We call it persistent memory because, like DRAM or the memory, you can access these technologies or update data in those kind of persistent memory technologies using load stores at byte grain, at the level of bytes. You don't require operating system to actually move data to the DRAM. And their performance is closer to DRAM, not exactly same. They are 3 to 10x slower, but still at nanosecond scale. There are many examples of such type of data technology, like Intel's Optane DC memory, Samsung's memory semantic SSD. There are other startups like Everspin's STT-DDR, and so on. Since they actually blurred the long-held distinction between memory and storage, this has also led to quite a bit of change in the software stack for the application that need persistence. And this has happened in many of the software stacks, like from data analytics to, say, persistent kilobyte stores to databases and so on. One thing to note is that persistent memory is not really replaces DRAM, it supplements the DRAM. The reason is, as we talked about, that although the persistent memory's performance is close to the memory, it's still 3 to 10x slower, and not all data requires to be persisted. Only a portion of the data requires to be persisted. So it doesn't make sense to actually use the persistent memory completely and replace the DRAM. What we found in our research is that while a lot of work has happened in the CPU software stack to actually get this persistent memory technology assimilated in the stack, what has happened is that while a lot of compute today happens on the GPU did not have a direct way to manipulate data that actually reside in the persistent memory. Okay. And this actually creates a lot of constraint. For example, if you want to actually compute on the GPU, you would actually compute in parallel. That is what the GPU is good at, as we talked about. But then if you rely on the CPU to persist the result of that computation on the persistent memory, then what happens is that the benefit of parallelism is kind of lost, because you would rely on the CPU to persist the computation that you did, results of computation that you did in parallel. And CPUs are not great with parallelism, not at the scale of the GPUs. There are other issues. For example, if you are updating or inserting elements of, say, a hash map in parallel on the GPU, until you do the computation, you don't know what are the elements that you will actually update in the hash map. You don't actually update the whole data structure. This can be true for a matrix too. For example, I'm actually showing some of the elements of the matrix. Due to the computation, you might actually update it, but you don't know upfront what entries would be updated. Since you are computing somewhere else on the GPU, and you have to rely on the CPU to persist the results of the output, what happens is that you have to conservatively write the whole data structure to the persistent memory. That leads to what is called the write amplification, extra writes. That actually degrades performance. And it also hampers the programmability because you now have to always think about, oh, something I would actually compute on the GPU, and then we then need to actually talk to the CPU to actually persist the results of that compute. So one of the key things that we did in our lab for the first time, that we enabled GPU programs to directly access and manipulate persistent memory without needing CPU. And this was the first time that somebody actually did it without requiring any hardware changes. Now, how did he actually did that? Of course, for that, we can't actually go into details. I'll actually provide the references of the papers that we published on that at the end of the talk. Whoever is interested can look into that. But I really like like working on this because we essentially did a lot of innovative jugaad of technologies. By that I mean is that we ended up taking advantage of existing hardware features that were not meant for GPUs to access persistent memory, but we actually tweaked it with the software help and made it to do what we actually needed to do. For example, there was technologies for the GPU to access or refer to data on the DRAM. We extended it to access the persistent memory too. Then the other problem is that whenever the software wants to persist some data, there is always volatile caches. And the software needs to actually ensure that it needs to actually guarantee the data actually is not residing in any of the caches, but actually has gone on to the persistent memory or the storage so that it can survive power cycles, right? For example, it can happen some results of some data that some of them have actually gone to the persistent memory, but the rest few of them, GPUs also have a volatile cache in that they might be actually sitting there. So not all data has been persisted. So to avoid all such situation, we actually took advantage of the facility that existed for CPU-GPU synchronization, and tagged it with some other technologies like DDIO that is actually used for IO caching to create the software primitives that you would actually require to make sure that the GPU program can ensure or guarantee that some data that it requests to be persistent on the persistent memory has actually persisted. Now, again, this is a very high-level view, but once you actually created this ability for the GPU program to directly update the data in the persistent memory, the next question becomes, like, what kind of applications that might actually benefit out of this newfound ability that we actually created. So we found there are three classes of application that benefits. Some of the same thing that we actually talked about that required fast persistent, like as we talked about Meta's RocksDB or LabelDB. Anytime you go to the Facebook or Instagram, those are the backend that gets exercised. Those can actually benefit from both GPU and persistent memory. Then we talked about checkpointing, DNN or HPC application. Those also can actually benefit because a lot of computation happens on the GPU. Now they can directly checkpoint to the persistent memory without talking to the CPU. And there is a new class of application that we call, say, fine-grained in-place updates for the graph applications, which I'll not be talking about here. But that's also a new class of application that you actually enable through creation of this ability that the GPU can directly manipulate data on the persistent memory. But one of the things is, anytime you actually create a new system, you also need to actually make sure that it is easily programmable. So for that, we started looking into, for each of this class of application, what is the key software primitive that they actually need. So in case of, say, a GPU accelerated database, as any kind of databases, they need logging. Logging is the, say, write-ahead logging. Logging is this mechanism where before you update some data structure that you want to actually update, you first take those updates and actually put it somewhere in the log so that you can actually recover later if something actually goes wrong during the update. Right? And then the second one needs checkpointing, and the third one needs internal persistence. We would not actually talk about that in details. So then what we actually did is that we actually created a new GPU runtime system for programmability. I don't want you to actually read all of this. The persistence, the key part is that it has all what the software, the application software would actually need to easily use the newfound ability of the GPU programs to persist its results of its computation to the persistent memory. And just to give you a sense of how much, how different interesting challenges comes up when you're trying to, design a new runtime system for the GPUs. Let's think about logging, right? Okay. And remember that when you're talking about GPU, remember that whenever we're actually talking about GPUs, it's all about computing in parallel. Okay. And let us assume there is a shared log on which all these threads wants to actually log. Since the execution would happen in parallel, they might actually try to actually log at the same time. If you are not careful, all these different threads running on the GPU can step on each other. So an easy way to solve this problem is to add a lock, right? But locks are pretty bad for GPUs because that kills parallelism. So using the GPU does not make sense anymore if you start using locks. Okay. So how do you solve that? So for that, we utilized our knowledge of how the GPU hardware actually works and how it is actually programmed. Since the GPUs have hundreds and thousands of threads running concurrently, they've enforced a hierarchy of threads. For example, you might actually launch work on a GPU with 100,000 threads. All those threads needs to be actually broken down in groups of, say, up to 1,024 threads, which are called thread blocks. Okay. So you have multiple thread blocks within those, that you have to actually create. And then within each thread block, there is something called a warp, a group of 32 threads that would actually execute in parallel. So what we did is that, and each of these threads, thread block, and a warp, they are uniquely identified by the hardware itself. Okay. So our key idea was since this is what actually GPU programs actually enforce, and this is how the GPU hardware actually works, what we did is at a very high level is to actually, reflect this log structure into the shared log itself. So each of these, say, thread block, the group of threads that are identified by the hardware, has their unique place in the log where they would actually put their results. Similarly, within this thread block, each warp has its unique place where they can actually log its results. Similarly, each of these threads within a warp, they have their own place, statically decided by their the identity of the thread where they can actually log. So what it means is that now you can actually do logging from the GPU directly to the persistent log that is in the persistent memory in parallel without taking a lock. That is what actually gives you performance. Ultimately, after we actually created this system where the GPU programs can directly access the persistent memory, and also created the runtime that can easily allow you to easily write applications for such applications. In summary, what it actually allowed is that it, for example, and this is without any required new hardware, it allowed, say, checkpointing to happen that is now 15 times faster. Or some of the databases we tested, this became 5x faster. And all this code, all the software actually open source. I'll provide you with links to all of that at the end of the talk. And that is what we actually mentioned, that this is how we took and software evaluation, whether there are a lot of software today relies on the GPUs, and then take a technology, which is the persistent memory technology, we put them actually together to create a new kind of system. Now we're getting a little bit on the next work that we actually did. That is the paper that is coming up in a couple of months in SIGMOD. What we then actually started doing, once we actually have this system, we started doing a more of a deep dive into commercial grade software, like, as we talked about again, like RocksDB. It's a persistent key value store, widely used. There is another version from the Google called LevelDB, This is widely used in many of the internet scale services because they are very efficient and simple to use. And we started looking into how we can actually really accelerate them while keeping all their rich features that is needed to support commercial applications. So they have a very simple primary interface where you have you can actually call a function called get and provide a key, and it will try to actually give you the value corresponding to that unique key. You can use set, which is given a key and a value, it would actually update the value that correspond to that key. What we also observe is that they also, all this, this commercial persistent key value store, they also have a lot of other operations that are needed to support wide range of applications, not commonly used, like delete range, compression, and so on. And there is a lot of background operations that actually happens, like data integrity checks. It will actually do a compaction of the basic structure, the log structured merge tree in case of RocksDB and level DB in the persistent memory, right? When we started analyzing where the time goes when you are actually running all these applications, then something new, something interesting we found out. We found out that most of the time, most of the complexity of the software is in these background operations and so on. But if you look at where the time goes, we found out that most of the time, even though these are actually persistent key value store, most of their time actually goes in manipulating in-memory data structures, the data structures that are in the DRAM. Also, they are persistent key value store. They support recoverability and so on. Also, non-negligible time actually goes in logging. But remember that thanks to the our work that we actually talked about before, we have a very efficient way to log from the GPU. So what we really did is create a system now that actually accelerates this key software stack called RocksDB. The full stack on both CPU and GPU through a judicious separation of responsibility between CPU and the GPU. Okay, so what happens is at a very high level, the performance critical parts of the RocksDB goes on the GPU that we actually identified, as I mentioned previously, and we actually accelerate that. While the background operation, non-performance critical ones, we keep it unmodified on the CPU. Why it actually helps? It actually speeds up. Why do you need to actually speed up? The RocksDB becomes now 18x faster. At the same time, it retains rich feature set of commercial software like RocksDB, which a lot of other internet scale services relies on. And there is minimal code modification. While I actually kind of simplified what at a high level what we are trying to do, it does present a lot of interesting new challenges. For example, say if you take this case of RocksDB, it gives you an interface to the upper level software that looks like each of these operations it executes sequentially. Of course, we cannot actually do that when you are accelerating it on the GPU. So how do you actually maintain the same semantics while also doing many of the operations in parallel? We use versioning, for example. And then, since you are actually executing at the same time on the CPU and GPU, how to make sure that the coordination is actually efficient. All of these details, we can't get into the details of all of this, but I'll give you references of if you are really interested in looking into deep into that. And all the software are open source as well. So with that, since we are actually run out of time, this is where I'll actually summarize. I hope I can actually, at least somewhat convinced you is that there is a value in looking into the software trends or the application trends, and also see how the technology is actually changing from the bottom of the stack. So you look from the top of the stack as well as from the top, bottom of the stack, and see what they can meet together and create a new, class of systems for, in this particular case, GPUs along with the new, persistent memory technologies to create, new opportunities for the software stack that, can utilize them. And for if anyone who might be actually interested in taking a deep look, you can, these are the references of the papers that we actually published on this topic recently, 3 of them. And all the software, as I mentioned, is open source, and anybody can actually try it. With that, I can now take questions. Thank you.